Yeah, hi, welcome everyone to this presentation prediction of frequencies from buoy measurements. My name is Thomas, and this presentation accompanies our recent publication of myself, authored by myself and Professor Balachandran from the University of Maryland in College Park. Just appeared this summer as of 2024 in Scientific Reports. So just to motivate the topic of freak waves or rogue waves are example of extreme waves and are defined as waves which are significantly higher than the neighboring waves. So just to picture it, here is a time series of sea surface elevation, so ocean waves. And we can see that for the majority of the time, the sea surface elevation remains rather limited, while we now see here a sudden large wave appearing, which also quickly disappears. So this is an example of an extreme wave or rogue wave, freak wave. Just to give you a bit of more of a graphical impression, here's a video of a freight ship in the ocean, and it's traveling through some heavy sea, but nothing out of the ordinary. And now, after this wave, we can now see here on the right-hand side that a large wave builds up, um, encountering the ship, and now it hits the ship. And from this video, we can already sense the sheer forces and pressures acting on the ship hull, which is clearly not ideal. So while this ship could continue its journey without any visual harm, others were not so lucky. So the loss of supercarriers and serious injuries of sailors and passengers have been linked to the occurrence of rogue waves. So this inspired quite some research efforts into studying and understanding the formation of rogue waves. And by now, two popular mechanisms have arisen. Um, on explaining how rogue waves occur in the ocean. So according to the first mechanism, rogue waves can occur to the superposition of elementary wave. Here, an elementary wave is given by a harmonic function, so the cosine function, which all the elementary waves all have their amplitude, their frequency, and the phase. While the amplitudes and the frequencies, one can measure those, the phases are generally unknown. And then one can encounter different scenarios. So if the phases are all appropriately aligned, one can observe a constructive interference at some point in time and then observe a large wave here. So this is, for example, a rogue wave. Whereas for another choice of phases, no outstanding wave is observed. And since the phases, so this which scenario is going to be observed depends on the phases. And since the phases are unknown, in this setting, the rogue waves are unpredictable. On the other hand, the nonlinear Schrödinger equation has been used to explain the occurrence of rogue waves. So this equation can feature the Benjamin Fair instability and also other type of breather type solutions, which could explain the occurrence of rogue waves. So those generally develop on slow time scales, so over very long time horizons. Just to give you a picture of uh, such a breeder type solution, we can see here that there is something developing in the wave tank here, that there's a large wave building up and causing the capsize of the ship here. But since those kind of instabilities develop over long time horizons, they should be technically, at least in principle, predictable. So what are rock waves now? Are they now predictable or unpredictable? So to predict, of course, means that one estimates if an event happens in the future or not. So for rock waves, this means what that means for rock waves, I'm going to show you on this two time series here. So now it's essentially based on the knowledge of time series, one needs to decide, one needs to answer the following question: will a rogue wave occur? So basically now, given this time series here, one needs to answer the question: will a rogue wave occur after the time series? which for the top time series, there's no rogue wave event after the time series ended. So the answer should be no. And in case of the bottom time series, the answer would be yes, because a rogue wave occurred after the end of the time series here in the blue in the green section. So if one tries to forecast predict those rogue waves, this implies that there is some sort of functional relationships between the waves prior to the rogue wave event and the rogue wave. And if this functional relationship exists, we can approximate it with universal function approximator, for example, neural networks. And that's what we are going to do in the next couple of slides. So we are now following two questions. So the first one is very fundamental. Are rogue waves predictable? And the second one is very practical. We just want to predict rogue waves. So to issue some sort of warning system for actual operations on the ocean. To do that, we need data, and we've utilized data provided by the CDIP, which is associated with the program run by the Scripps Institution of Oceanography in San Diego. So on their webpage, you find data from a huge buoy network, which is primarily located at the shores of the continental US, but some buoys are also in the Pacific. And the sampling frequency of 1 Hertz is beneficial to work with this kind of sampling rates, because 1 Hertz allows us to resolve individual waves, such as the rogue wave events we are after. Overall, we have about 880 years of data if we stitch all measurements of all buoys together. So this is quite a lot of data. And this data we scan now for rogue waves. And by the way, you can find the compiled rogue wave data sets all online here under this link. And now there are different definitions which all relate some kind of local wave height, which can be either the wave height or the crest height, to an average sea state, an average wave height, which is, for example, the significant wave height. And if this fractions surpasses a certain threshold, this wave is qualified as a rogue wave. And depending now on the different type of definitions, we end up from out of this 880 years of data, we extract about, let's say, 20,000 rogue waves, or for this threshold, a little more, about 170,000 rogue waves. And then we prepare the data set as to forecast those waves. So we feed data into a model. Most importantly, the data we feed into the model does not contain any rogue waves. So these are time series taken prior to a rogue wave event, and the time span between the last sample and the rogue wave event is the advance warning time. And within this data sets, we include samples which are not followed by rogue waves, so this top time series, for example, and we also include samples where a rogue wave occurs afterwards. So this implies that now my time series are naturally labeled into two classes. So the first class would be no rogue wave will occur, and the second class is yes, rogue wave will occur. So this reformulates our time series, so the forecasting of rogue wave problem, into a time series classification problem. And to tackle this problem, we utilized neural networks with LSTM cells, and which is a bunch. We use a deep neural network with a number of LSTM cells, and also a dropout layer to avoid overfitting. The whole network is implemented in TensorFlow, and we utilize the automated hyperparameter tuning algorithm RayTune. You can find all these networks also online, so you don't have to you can recapitulate all the training we did in this work. Now containing the results, so the forecast can be either rogue wave will occur or rogue wave will not occur. Also, the truth can be rogue wave did occur and rogue wave did not occur. So this gives yield to 4 combinations, which are most appropriately summarized here in this confusion matrix. So first of all, for example, the true negative, which says that the truth, no rogue wave did occur, and also our prediction said no rogue wave did occur. So here we accurately predict no rogue wave will occur. On the other hand, for example, a false positive would indicate that no rogue wave occurred in the truth, but our prediction was a rogue wave will occur. The true positive is the number of the correctly predicted rogue waves by our neural network. And we can see that we are able to predict 3 out of 4 rogue waves from in the testing data. And the overall accuracy of our networks is about 75%. So 75% of our corrections of the network is correct. In practice, one tries, of course, to extend this advanced warning time. So this is an advanced warning time of 1 minute. And if we try to extend it, the accuracy drops as expected because longer forecasting horizon is generally more challenging to forecast. And the accuracy drops from about 75% to 70% within 5 minutes. So this is for the rogue wave definition where the wave height exceeds the significant wave height by a threshold of 2.2. We also have looked at the alternative definitions where we have a threshold of 2, or the rogue wave definition where we have the crest height as a wave parameter here. And for those kind of data sets, the accuracy drops a little bit to 70% compared to the 75% earlier. Now, consider a scenario. We have trained our network with this buoy data, but when it's interested to forecast ocean waves at a specific location, which is generally not included in the network. So the question was now, can we utilize our knowledge we have or the trained network also for other buoy locations? And to emulate this application scenario, we have excluded one buoy from the training data. So excluding the buoy 67 here, which is off the coast of LA, the distance to the nearest buoy is about 70 kilometers, and about 350 rogue waves have been measured at those specific locations. Now we exclude all these waves from the training data set and retrain the network only on all other buoys from the network. And the accuracy is about 75%. And now we test our network on data from this buoy location, which it has never seen in any stage. And we observe that the accuracy is again about 75%. So 3 out of 4 rogue waves are correctly predicted. So this implies that the model extrapolates very well to unknown buoy locations. And we tested this further by considering shallow water. So the prior buoy was about 260-meter water depths. The same story holds also for shallow water buoys, where other physical aspects come into play. Again, we observe an accuracy of about 75%. And last but not least, we have considered an extremely remote buoy where in the middle of the Pacific. There, the closest buoy is several hundred kilometers away, and it's also an extremely deep water, more than 4,000 meter depth. And also for this case, we observe an accuracy of 75%. So our model extrapolates very well to unseen buoy locations. So what the network has picked up seems to be indeed generalizable. Last but not least, we have considered another scenario. So far, the prepared dataset always consisted equal amount of rogue wave samples and non-rogue wave samples. In reality, the samples which are not followed by rogue wave will be much more than the samples followed by rogue waves. So for the dataset from the CDIP, about 0.1% of half-an-hour intervals are contain a rogue wave. To emulate the scenario, now we have enriched the number of non-rogue wave samples in the testing data. And again, we observe an accuracy of about 75%. where now the two top quadrants, of course, overwhelmed because this is where no rogue wave was observed, which is the number of samples is just is just much higher than the samples of rogue waves. But the overall accuracy is about 75%, which tells us that our network can be employed in more realistic scenarios where the number of samples of non-rogue waves are just overwhelming. So just to conclude, I've showed you a way to train a neural network to predict rogue waves. So the accuracy is about 75%, and the forecasting horizon is about 1 to 5 minutes. We further learned that the neural networks extrapolate very well to other employment scenarios, either something emulating the real ocean or other buoy locations. For the future, we are thinking about ways of improving these forecasting accuracy and horizon further. One way to do this, for example, is by incorporating spatial information, because the buoy location is a single point observation. We have not incorporated any spatial information in the network, but in reality, waves travel through the ocean, so they do have spatial information. So this could further improve the accuracy and forecasting horizon of our approach. With that, I'm at the end of this presentation. If you want to learn more, you're very welcome to check out our publication. The code is on GitHub, and the data you will find on Zenodo. You're also happy to reach out, shoot me an email. I'm looking forward to it. Thank you very much for listening.